I'm going to begin discussing Anabranch systems or Anabranch floodplains in a historical and geomorphic context, and then moving on to discussing our approach to implementing Anabranch in a restoration phase in swamp, present some of the design features that we used in putting in Anabranch wetlands, and finally discuss the wetland performance in reducing nutrient loads from a stream watershed, restored watershed. Okay. So let's begin with a definition for those of you who have not heard the term Anabranch before. Anabranch is a stream that has multiple channels or flow paths that split at one point and then rejoin further downstream. Now what separates Anabranch systems from like braided systems or grading systems is that the channels are separated by stable low islands, and so they retain their shape over long periods of time. And if we repeat this anabranching pattern over several scales or multiple levels, then we use the term anastomosing. Okay. So talk a little about the current floodplain conditions in the Piedmont. A lot of you have seen the Walters and Merritt paper talking about the effects of mill dams. But to review that a little bit, in a lot of Piedmont floodplains, we have as much as several meters of legacy sediments that have accumulated, and those are accumulated both from severe upland erosion due to agriculture, especially during the 17th and 18th centuries and into the early 19th century, and also to some extent in some areas the effects of mill dams, which have exacerbated this process of sediment accumulation on the floodplains. Okay. Let's try it. Well, I don't know. Mm-hmm. So the effect of that has been in a lot of cases to produce overbank flood intervals of 1 to 2 years, which is often used as a design criteria for restored wetlands. And that limits floodplain connectivity. And as a result, we've had reduced nutrient retention efficiencies of many riparian wetlands due to one thing, load limitations. So we're not getting nitrogen and phosphorus up onto the floodplain that often, maybe every 1 to 2 years. So that right away limits the water quality functions of floodplains. And when it does happen, when we do get water up on the floodplain, it's only there for a short period of time, basically during the flood peak, especially due to flashy hydro periods during flood events. And finally, we have a lot of problems with channel incision caused by more recent urbanization that exacerbates these trends. So contrast current conditions with historical conditions, and these are the conditions described by Walters and Merritt again. The current connectivity limitations were not typical of pre-settlement floodplains, this pre-settlement floodplains more characteristically had a forested stream network with small streams, low vegetated islands within the flood zone, and typically many small, again, anabranching and chain of pools streams with frequent overbank flow and extensive alteration by beaver dams.
Okay. This is a picture that's drawn. Do they have they discovered a place where it still exists so that they know that there's a live example of what the model shows?
Well, I can think of a few places where I think it still exists, especially in Durham. There's one example of the New Hope Creek bottomlands path where I think that there's certainly an example of a wetland that has really strong connections and secondary channels. If you wouldn't technically consider it anabranching, it certainly has a strong connection to the main channel, and during small flood events you get water flowing up onto the floodplain. And I can think of some examples in Duke Forest where they're leaving beavers along where it's maybe starting to reestablish. Yeah, okay.
Michigan and Wisconsin's been just inundated with beavers. I mean, they flooded out half of one national forest. But in Michigan, at the Houghton Lake, Michigan Biological Station, where they have about 20,000 acres, there are 2 rivers that have got 5 and 6 beaver dams where it's all, you can see exactly, you take a glass
So I'm borrowing a figure right out of Walters and Merritt's paper here, showing, again, our Holocene wetlands here that have been covered by our legacy sediments, and shows an example here with a black band at the toe of the stream bank here, and again, several meters of accumulation of legacy sediments on top of it. So you can advance, Kurt. Yeah. So we've said that this is, the Walters and Merritt paper have demonstrated that this is widespread in North America, and we found some other papers that show this was also happening in pre-settlement conditions in Europe. So the natural state of lowland rivers of much of northwestern Europe was multi rather than single-braided anastomosing, I have trouble with that term for some reason, and anabranching. So dynamic, low to medium energy pre-deforestation floodplain were dominated by disturbances like wind throws, beavers, and large woody debris, and that the floodplains have changed dramatically due to siltation of secondary channels and stabilization of cohesive alluvial banks formed from eroded agricultural soils. So pretty much the same processes are going on in Europe as are happening, have gone on in Europe, is happening here. And some examples of papers from different areas in the temperate zone of North America and Europe, including the Pacific Northwest, and Kurt Wegman at NC State is starting to look at this in North Carolina. So, back to your question a little bit maybe, is why are there so few anabranching wetlands today in the Piedmont? So part of that is because of the deposition of the legacy sediments that we were just talking about. And another part of that is that when we remove these mill dams, in a lot of cases, that we tend to have the formation, we tend to cover up multiple flow paths and floodplains with these legacy sediments, several meters of legacy sediments, and then when these mill dams are either removed or they fail, we tend to have a tendency to develop a single channel stream in the unconsolidated sediments upstream of the dam. And we also, by removing the dam, in a lot of cases, we have a sudden increase in the slope of the stream valley. And so we tend to have a process of incision going on. So you can move on. This is a model proposed by Martin Doyle, who was at UNC and is now at Duke. We have several stages. We have a pre-removal stage where we have flooded alluvial sediments upstream of the dam, then a stage B where we lower the water surface, and finally moving on to the beginning of degradation when we remove a dam and remove water from the upstream sediments, and we start with the development of head cuts that start to move up through the legacy sediments, or the sediments upstream of the dam, and a stage of degradation and widening. And finally, we start to move into a stage of degradation and widening, and we obviously have a very steep stream bank cut through these sediments upstream of the dam that are prone to bank erosion. And eventually we end up with a quasi-stable equilibrium at a final stage where we have essentially an abandoned terrace and a stream cutting itself a new floodplain down inside a channel and a somewhat stable channel at the bottom. So other factors contributing to the loss of anabranching wetlands are loss of hard points on floodplains that tend to stabilize these islands, these stable islands that divide our multiple channels. One of which is the loss of really large old growth trees that help stabilize the islands. Also, with the loss of really big trees, we're also losing some of the large log jams that were on the floodplain that were causing the accretion of sediment, alluvial deposits around these log jams, and that resulted in high points on the floodplain. We also have a reduction in the channel division or avulsion events. So we have humans going in and actively straightening channels. We have active stream incision in areas that are undergoing urbanization or dam removal. Log jam removal from the channels themselves. And we tend to like to maintain flood conveyance and navigation, so we go in and remove log jams. And we're controlling beaver, so we're preventing beaver from building dams on floodplains that would contribute to the development of multiple channels. And finally, just human preferences. We like single channels for a bunch of reasons, some of which is aesthetics. We just like to think of a mountain stream or a trout stream. Again, flood conveyance, in some cases property boundaries, and especially in early settlement times, they tended to use single channels to define property boundaries, and so they like those. Agricultural production, it's a lot easier to plow a field with one single channel at the edge of the field than it is to plow a field that has multiple stream channels running across a floodplain. And finally, things like trout fishing. We like a nice single channel with a nice clear canopy for fly fishing or whatever. So human preference has contributed a lot to this. So this picture shows us what a pre-settlement floodplain with large trees going on it might have looked like. This is an example from Three Sisters Swamp on the Black River with old cypress growing in that area. And so we have a small channel that's readily connected to the floodplain, and we have these large trees that help stabilizing the channel. So moving on, there's been some authors like Kluwer and Thorne here that have tried to expand existing channel evolution models to bring in the concept of anabranching wetlands and pre-settlement conditions. And typically, the channel evolution model starts with stage 1, runs through degradation phases, degradation and widening, and then aggradation and widening, and ends in a quasi-equilibrium here in stage 6. What they've added is a precursor stage here that represents pre-settlement conditions, stage 0, or anabranching condition. And then I've added notably two stages at the end here, stage 7, a stage of a laterally active channel. And finally, we end up back where we started again with an anastomizing channel, our floodplain system. I'm going to move on to the next. And they also evaluated the functionality of these different stages of stream evolution. And what cut to the chase here is that what they really found was that the most functional systems are the anastomizing streams in terms of things like water quality function and habitat support, followed closely by a stable single thread channel. All right, and then as we move through processes of degradation and aggradation, we get a really substantial loss in function of the stream system. And as it starts to recover, moving back into quasi-equilibrium and laterally active and finally anastomizing systems, we get a recovery of function. And again, we just summarize this in terms of categories of high, medium, and low. Now I just point out in terms, especially what I'm interested in talking about today is things like water quality and flood storage, is that the anastomosing channels have the highest function, followed by meandering systems, and then things like braided systems are much lower.
Where I've seen really braided systems, it seems to be this place where you get the most instability.
Braided systems are basically systems that are grading, and the channels are very unstable and are moving laterally. They might change from one flood to the next. So moving on to the question of whether anabranching systems are really a valid model for restoration. Part of that comes down to perception. I mean, one example I looked at, we recently had Margaret Palmer coming from the University of Maryland and talking about different types of stream restoration in terms of their water quality. She looked at more traditional natural channel design approaches. She looked at more hard engineering approaches. And she concluded that those approaches didn't do much in terms of water quality improvement. But then she had an example of a couple wetlands or a couple restoration projects that were stream wetland complexes, which is kind of what we're talking about today. And she concluded that these systems actually did something in terms of improving water quality, but then she concluded that, but even though they function well, it's not really restoration because these are not natural systems. So she basically discounted these stream wetland complexes because she couldn't find examples of stream wetland complexes in Maryland that would be a natural model for these systems. And so the question comes down to, do you have to be able to find stoneflies in a restored system for it to be a successful restoration? And must we also have riparian systems that have attributes of pool riffle systems for it to be a successful restoration? And for example, we found this mass of salamanders in our Anabranchian system, and would are stoneflies necessarily better than this in terms of habitat function and water quality indicators? Now, I might point out that right now in Ohio they're working on amphibii or amphi-IBI, which is a biological index of biological integrity based on amphibians. So, I mean, maybe stoneflies aren't necessarily and benthic aquatic macroinvertebrates aren't necessarily the be-all and end-all of restoration. Perception's also influenced by geomorphology. I have a quote from Montgomery and Paget, where it's no doubt about it wood complicates fluvial geomorphology. It messes up nice tidy streams and complicates quantitative analysis. And basically it comes down to the conclusion that it's no coincidence that modern fluvial geomorphology developed through the study of channels lacking substantial loads of woody debris. So really all the systems that we've used by Leopold, and I think Leopold's done great work, but maybe it's a little bit skewed in terms of looking at stream reaches that lack log jams and woody debris. So moving on to talking about what we've done in swamp, and you've seen this figure yesterday, and I think we talked a lot about locations, but we're just here in the upper reaches of Sandy Creek in the Cape Fear watershed in Durham County, North Carolina. And this is the upper Sandy Creek watershed, and what we're going to be focusing on today is the watershed of Phase 4, and you can click that one more time, and that's about a 60 hectare catchment within the swamp watershed. And so just to orient you a little bit again today, this is where we parked yesterday up here about where the P in swamp is, and we walked down this trail. Then we talked about the impoundment and walked and came down on the floodplain here by WT6 and walked back up around to look at Phase 3 and then back to the parking lot. And what we're going to be talking about this morning and visiting this afternoon is here in Phase 4. So this is what the stream looked like before restoration. This is a typical incised channel with toe erosion and bank instability, and the banks slumping into the stream channel in some parts. In other parts, it's in a grading channel where we have sediment accumulating being stored within the channel. This is Jonathan Bills, who's sitting right back in the corner here, standing in the upper reaches of our restoration project, and you can look at the bank heights here and look how incised it is. So this is a system with little connection to the floodplain. And as we move downstream, the level of incision decreases a little bit, and the banks are not quite as deep, and there's a little bit more connection with the floodplain, but it's a grading. So that's the background, and now I want to talk a little bit about some of the sites that we visited in Duke Forest that kind of inspired our Anabranching approach to restoration. So there's some areas in Duke Forest where the beavers aren't bothering anybody, and nobody's bothering the beavers, and they're going about their dam building, and people are leaving them alone. And then in this particular example, a beaver built a dam and plugged up a nice incised channel here, and you can advance the slide. And what ended up happening is that we had, just upstream of the beaver dam, we had water being pushed out of the stream channel and up onto the floodplain, and creating a second flow path across the floodplain, and eventually coming back into the stream channel downstream after spreading across the floodplain, and having some water quality benefits. This is what the inflow looks like, the main channel in the background up here of Mud Creek. The beaver dam's right around here somewhere, and there's a notch in the natural levee where the water's flowing through and up onto the floodplain. And this is what it looks like in the backwater area with stream water spreading out across the floodplain. And eventually, it becomes constricted again and flows back into Mud Creek. So now we move on to talking about how we implemented some of this in Phase 4, and implementing our Anabranching concepts. And you can go ahead and advance. Next, okay. So this is our restoration objectives. The first one was to increase the hydrologic loading of the floodplain wetlands without substantially altering the cross-section of a restored stream channel that was adjacent to our restored wetlands. So we wanted to maintain flow in the single channel, the base flow between storm events. So for several reasons, for habitat reasons, and we'll get back to this in a minute for regulatory reasons. But in particular, we're looking at increasing nitrogen removal efficiency of these created wetlands, and we're really focused on nitrogen in this case because of TMDLs in Jordan Lake, where they identified nitrogen as a primary driver of water quality issues in the lake. So we're a little bit focused on nitrogen here, but we really wanted to increase the frequency of nitrogen loading onto the floodplain. So we wanted to increase it from every 1 to 2 years to more frequently. And we'll see in our experimental design that we can actually manipulate how frequently this happens. We also wanted to increase the contact area between soil and surface water, which is, to some degree, a single thread channel has a really limited area of contact between water and soil under most conditions and most of the time. Increased retention time. How long is the water held on the floodplain or in the stream channel before it reaches Jordan Lake? Another goal was to retain soil organic matter as a substrate for microbial processes, and we were particularly here focused on the idea of denitrification, that if there's no organic carbon in the soil, that's going to limit your rates of denitrification. So we wanted to try and at least think about soil organic carbon when we were designing our wetland system. Increase coarse woody debris and create microtopography, and we'll see when we were looking at some of our natural reference wetlands that this microtopography turned out to be pretty important in terms of creating hotspots for denitrification. Well, actually, this one is, our watershed is a mix of, it has actually commercial land use in the headwaters. There's a school and maybe a strip mall. There's a small part of a cemetery. And then there's quite a bit of low density, suburban development within the watershed. So it's coming from lawns and it's coming from typical suburban sources. So looking at comparing traditional, we're talking about the interface between surface water and groundwater, in other words, a hyporheic zone, and that area of contact between soil and surface water. And we compare the idea of what's going on in a traditional restoration with a single channel, where we have the channel filled to bank full with water, and then we have the zone of the hyporheic zone where there's exchange between water coming from the stream channel and the groundwater. And that's really a relatively limited area, surface area of the hyporheic zone, and also the volume of the hyporheic zone is fairly limited. But we find, at least conceptually, when we start moving water up onto the floodplain with our anabranching design, that we are actually spreading out or extending the hyporheic zone up onto the floodplain, increasing both the surface area of the hyporheic zone and the volume of the hyporheic zone. So that's going to be important in terms of water quality functions like denitrification. So this is just a cross-section of our stream valley, exaggerated vertically, obviously, with a meandering stream channel intersecting our cross-section at this point, meandering back across the floodplain and coming back and intersecting our cross-section again at a lower elevation. And if you want to just hit the button one more time. And the key point here is that what's driving water flow through our anabranching system is the change in elevation between the invert of our swale that's intercepting flow at the base of our stream channel here. And the swale looks like a pipe. It could be a pipe, but in our case, it's a swale. And that change in elevation between the invert of our pipe or swale and the outflow of our berm right here at the other end of the wetland. So that change in head is going to be important for driving flow through the wetland system. To look at it in another way,